It's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about how to find the determinant of a matrix. That's right, this is an exciting video on an exciting topic, finding the determinants, and you and I are going to be going through this together, and I am so excited for this opportunity. How about we start with you showing your appreciation by clicking the subscribe button to the YouTube channel Fort Bend Tutoring, and if you will be so kind as to click on that bell notification so that you can be notified when we're uploading new and fresh content for you. All right, guys, I have a lot to cover today, so let's get started with the features of this video. First of all, obviously, we'll be talking about determinants, and I have examples showing you how to find the determinant of 2x2 matrices, 3x3 matrices, 4x4 matrices, and I'm including multiple strategies for each type of problem. This is a feature-packed Fort Bend Tutoring video, guys, that I can't wait to dive into. Let's continue. This page shows one of the strategies that we'll be implementing in solving 2x2 matrices as well as 3x3 matrices. It is the multiply and subtract method, and I am showcasing that process here in this 2x2 matrix. And when I say 2x2, guys, I'm talking about the fact that I have two rows. The horizontal elements are called the rows, whereas your vertical elements are your columns. So this is a two-row, two-column matrix. That's right. And in order to find the determinant of a 2x2 matrix, you simply multiply the elements A times D, and you subtract from that the product of the elements B and C to end up with your determinant value after having AD minus BC. And then for your 3x3 matrices, notice that we have three rows, we also have three columns, and we'll be also multiplying and subtracting, in this case, the diagonals of the 3x3 plus two additional columns that we will create for finding the determinant of a 3x3 matrix. Oh yeah. So here I have the result here, right here in a red box. So let's continue on, guys. We have problem number one. And in our problem, we have a 2x2 matrix, once again, meaning two rows, two columns. And the name of our matrix is A, and it contains the elements 3, 2, 7, and 4. Whereas the symbolism here, where it says find the determinant of A, notice that these vertical bars around the name of your matrix is informing you that they want you to find the determinant of that matrix. In other words, this is the operator when you're dealing with matrices that lets you know as a student that you are going to be finding the determinant of that matrix. And because we're finding the determinant, I can rewrite this problem by showing that this can be rewritten as the determinant of the elements 3, 2, 7, 4. And then, and using the multiply and subtract method, I'll be multiplying 3 times 4 and then subtracting from that the product of 2 times 7. All right, so first I'll be multiplying the elements on this diagonal coming from the bottom right to the upper left, and then I'll be subtracting from that the elements that I'll be multiplying from the bottom left to the upper right. So therefore we have 3 times 4, which is 12, minus 2 times 7, which is 14, to get a result of -2, and we're going to red box our answer just like that. And that is how fast you can find the determinant of a 2x2 matrix, guys. All in a nutshell, we went ahead and multiplied 4 times 3, then subtracted from that the product of 7 times 2. We wrote out our steps, combined our terms, ended up with our result of -2, and done. That is the multiply and subtract method for a 2x2 matrix, guys. And now let's talk about some fun facts about determinants. I have fun facts sprinkled throughout this entire video, guys, so make sure you're paying attention to those because these are fun facts from Fort Bend Tutoring. Number one, if the entries of any row or any column of a determinant are multiplied by a non-zero number k, and the result is added to the corresponding entries of another row or column, the value of the determinant remains unchanged. This is something I'm going to be utilizing in the second strategy that I'll be giving you guys for many of the examples that we have in this video. Let's check out another fun fact. Fun fact number 2, if any row or any column of a determinant is multiplied by a non-zero number k, the value of the determinant is also changed by a factor of k. Because this particular fact affects the outcome of our determinant, I'm going to try my best not to use this one. What I'm going to be implementing are strategies that will not change the result of the determinant, so I will have less to remember as I'm moving through these problems, guys. Moving on to fun fact number 3. The value of a determinant changes sign if any two rows or any two columns are interchanged. Once again, by swapping out rows or columns, you're changing the value of the determinant, meaning that me personally, I'll be avoiding this particular rule in the strategies that I'll show you today. It's not that you can't do these strategies successfully. It's just that I want to minimize the process as much as possible, okay? So let's go ahead and look at fun fact number 4. Multiplying the diagonal values in a triangular matrix or a diagonal matrix results in the determinant of the matrix. So this is really interesting, guys. Basically, what I'm giving you at the bottom of your screen here is I'm giving you examples of triangular matrices first. Notice that underneath this diagonal here, this is called your main diagonal, that you'll have nothing but elements that are zeros underneath that. This is a triangular matrix. Then, if you look at the second situation we have, all right, this, once again, I'm highlighting the main diagonal of the matrix, and above the main diagonal, all of your elements are zeros. Both of these two matrices are triangular matrices. If you combine this into a matrix where you have nothing but zeros beneath the main diagonal and above the main diagonal, you're dealing with a diagonal matrix. So in these 3 scenarios, in order to find the determinant of these matrices, all you have to do is multiply the elements in the main diagonal together to find the determinant. So for instance, in this middle triangular matrix, all I would have to do to find the determinant is multiply 1 times 3 times 6. Yeah. 18 would be your result, guys. This is going to be definitely something I'm going to be using as a strategy in this video today, okay? Let's go ahead and check out number 1 again. So in problem number 1, guys, we have once again matrix A with the elements 3, 2, 7, and 4. And because I want to find the determinant of A based on my instructions right here, I'm going to start out with the elements of A and my symbol for finding the determinant. That's right. These 2 vertical bars here are going to let everyone know that I'm attempting to find the determinant of these values here from the matrix A. So what I'm going to do is I'm going to create either a triangular matrix with zeros on the bottom, or I'm going to go with a triangular matrix with zeros above the main diagonal. Or I can make a diagonal matrix with zeros above and beneath the main diagonal so that I can just simply have those values in the main diagonal to multiply and not have to worry about anything else. Well, in many cases, guys, I listen to Lazy. And Lazy is telling me that I'm just going to do a triangular matrix and have zeros either above or beneath the main diagonal. I'm not going all out and coming up with a diagonal matrix with zeros above and beneath the main diagonal. Therefore, looking at our 2x2 matrix here, I think it's going to be easy to put a 0 right where this element 2 is. So I'll be multiplying -1/2 times row 2 and then adding that product to row 1, placing the result in row 1. So what this does for me, this allows me to multiply another row besides the one I'm trying to replace with any non-zero value k that I want, and then add that to the row I do want to replace, and it will not change the result of the determinant. That's why you want to make sure you're doing all of your multiplication with a different row than the one that you're replacing, okay? So notice I'm replacing row 1, but I'm not doing any multiplication to row 1. I'm just going to add the result of me multiplying another row to row 1 in order to replace it, okay? So what does this mean for us? This means that row 2 will go unchanged. So I'll bring down the 7 and the 4. And now I'll follow my row operation here, and I'll be multiplying -1/2 times 7 to give me -7/2, and then adding that to row 1's value, which is going to be +3. But in this case, I'm going to rewrite it as 6/2 so that I can combine it easily. This gives me a result of -1/2. So this is going to be the first element in row 1 after doing my row operation here. Then we'll be multiplying 4 times -1/2, which gives us -2, and then -2 plus 2 gives me the 0 that I wanted all along. So now that I have my triangular form here, because notice I have my main diagonal with zeros above the main diagonal. This is triangular form. And with that, I can go ahead and multiply the elements of the main diagonal to find out the determinant. Therefore, the determinant of A equals to -1/2 times 4, which gives us a result of -2, and done. Red, box it. That's it, guys. So notice that by changing the original matrix into a triangular matrix, we only had to multiply the elements of the main diagonal in order to get our result. You're going to find out that I am really digging this second strategy right here, guys. And many of you, as students especially, may think that there are too many steps involved in doing this method. However, the greatest benefit of doing this particular strategy is that you can do this strategy with any square matrix. So any 2x2 matrix, 3x3 matrix, 4x4 matrix, 5x5 matrix, into infinity, this strategy will always work. You won't have to adjust the strategy to solve problems using this second strategy of rewriting the original matrix as a triangular matrix and then multiplying the elements of the main diagonal. That will always work, and therefore I'm really excited about this second method here, guys. Okay, let's move along. All right, guys, I wanted to remind you to please donate to Fort Bend Tutoring. You'll find a donation link in the description box and on the about page of our YouTube channel, Fort Bend Tutoring. Every donation that you give allows us to bring you more free content from Fort Bend Tutoring and myself, Mr. Whitt, guys. So thank you to all of you that have been donating, and thanks to all of you that will. We really, really appreciate that. Let's keep it moving. Here we have problem number 2, guys. And in problem number 2, we have a 4x4 matrix. That's right. We're dealing with 4 rows as well as 4 columns in problem number 2. And because there is a convoluted strategy in order to solve the determinant of a 4x4 matrix, I'm going to stick with the second strategy on this particular problem, guys. And that strategy is, as long as we have a triangular matrix, which we do, by the way, all we have to do is multiply the elements of the main diagonal. So this particular problem, I'm only going to show you one way to do it, and that is simply multiply the elements of the main diagonal. So in order to find the determinant of this problem, we'll be multiplying 3 times 1 times -5 times 6. There you go, guys. So multiplying this out, we'll end up with 3 times -30 to end up with a result of -90, and done. Red, box it, people. Just like that. That was example 2. Once again, we had a triangular matrix with nothing but zeros underneath the main diagonal. So in a situation like that, just multiply the elements of the main diagonal, and that's the determinant, guys. Done and done. Let's keep it moving. Here, I just wanted to remind you guys that I'll be focusing on 2 strategies in this video. One will be multiplying and subtracting as we did in our very first problem, and 2 will also be multiplying the main diagonal of a triangular matrix. All right, so just keep in mind that many of our examples going forward will have 2 strategies displayed in order to solve them. Okay. So here we have problem number 3. And in problem number 3, when you have a 3x3 matrix, in order to use the multiply and subtract method, the first thing you want to do is you want to rewrite the first 2 columns. That's right. You want to rewrite 1, 0, -1, as well as -4, 10, and 2 to the right of the matrix. And notice that they're already looking for the determinant because we have the vertical bars here. That is telling you that the operation in play is finding the determinant of the matrix. So I'll be rewriting our first two columns, 1, 0, -1, as well as -4, 10, and 2. Notice how I simply rewrote the first two columns to the right of our existing matrix. Now we'll be multiplying up to the left these three diagonals that contain three elements, and we'll be adding them together. So for instance, I'm going to be multiplying 1 times 10 times -2 plus the product of -4, -12, and -1. And I'll be adding to that the product of 3, 0, and 2. And then I'm going to subtract from that the products of the diagonals rising to the right. These products that contain three elements will be subtracted from the first three products that we created. That means that I'll be subtracting -1, 10, and 3. And I'll be subtracting 2, -12, and 1. And I'll also be subtracting -2, 0, and -4. So what I was doing there was I was taking these diagonals here going up to the left, and I was multiplying those elements together. Then I came back and I was multiplying these elements together. All right. So that gave me my diagonals going up toward the left that I added together. Then I took all of the diagonals going up to the right and multiplied those together, as well as subtracted each of those products in my process here. So as you recall, this strategy is part of that multiply and subtract strategy. So we had our multiplication and we also had our subtraction involved as far as the second set of diagonals. Now to multiply and simplify, guys. We'll have 1 times 10 is 10. 10 times -2 gives us -20. Then multiplying -4 times -12, that gives you +48. 48 and -1 give you -48. Then we'll be multiplying 3 times 0 times 2, that gives you 0. Then we'll be finding the opposite of -1, which is 1. And 1 times 10 is 10, and then 10 times 3 gives you 30. From here, you'll have -2 times -12 gives you +24. 24 times 1 is 24. And then finally, you'll have the opposite of -2 is 2. And then 2 times 0 is 0. And 0 times -4 is still 0. So that means that we'll be combining together -68 as well as +54. And when we get our result, you'll end up with -14 as your answer. Red box it. Here we are with our red box, and that does it for the multiply and subtract method for problem number 3. Let's move on to number 3 again, but this time we'll be using the main diagonal to multiply the elements in our triangular matrix that we'll be creating. All right, so for problem number 3, notice that we have a 3x3 matrix, and what I'm looking for is the easiest way to get a triangular matrix, guys. That's all I'm concerned with. No more, no less. What's the fastest way to get a triangular matrix? So what I'm going to start out doing is recognizing that if I just simply add row 1 to row 3, I'll get a 0 down here. Okay, so that'll be my first move. I'm going to have row 1 plus row 3, putting the result in row 3. So therefore, I'll bring down the first row as it is because nothing's changing there. And the second row is not changing. So I'm going to bring that down too. And then from here, 1 and -1 combine to give me 0. -4 and 2 combine to give me -2. And then 3 and -2 combine to give me +1. So that completes that row operation. And I've just created another 0 beneath the main diagonal here because that's all I want. Now I just need to get one more 0 underneath the 10 here in the middle of our 3x3 matrix. So in order to get this -2 to become a 0, I'm going to use the following row operation. I'm going to have 1/5 row 2 plus row 3, putting the result in row 3. So this means that once again, only my third row will change. So I'll continue to bring down the first two rows as is. I have 1, -4, 3, as well as 0, 10, negative 12. And then as far as the third row is concerned, I need to divide every term in row 2 by 5 and then add it to the corresponding element in row 3. So 1/5 times 0 is 0, and 0 plus 0 is 0. And then a fifth of 10, or 1/5 times 10, gives me 2. And 2 and negative 2 give me 0. Then finally, y'all have negative 12 times 1/5. So that'll be negative 12 fifths. I want to add that to 1. Well, isn't 1 just 5/5, guys? If we combine these two values together, you'll end up with negative 7/5. And this gives me my result right here. So now what we'll do is we'll multiply all of the elements of the main diagonal. So remember, our main diagonal is right here. And multiplying this out, you'll have 1 times 10 times negative 7/5. And you should know that 5 will go into 10 twice, right? And 2 times negative 7 gives you a result of negative 14, and done. Red, box it. Done and done, guys. That is using the main diagonal to find the determinant once you have a triangular matrix. And that's problem number 3. Our next FBT fun fact shows us this. If all the entries in any row or any column equal 0, the value of the determinant is 0. Good to know. So if you run across a matrix that has a row that's all zeros or a column that is all zeros, don't waste your breath doing anything further than writing down 0 as a determinant. Okay? That's a good fun fact to know, guys. All right, and I would want to remind you guys to set up a paid online tutorial today with Fort Bend Tutoring, FBT. And I, Mr. Whitt, can assist you in your homework or preparing for a quiz or an exam or even a final exam. Just go ahead and give us a ring, a text, or just go ahead and go to our website at fortbendtutoring.com to set up a paid online tutorial today. All right, guys. Here we have problem number 4. Once again, we are dealing with a 2x2 matrix. The directions, of course, are to find the determinant for matrix D. So for matrix D, guys, the first thing I'm going to do is I'm going to go ahead and rewrite this as negative 1, 2, 6, and 4 with our symbolism showing that we are finding the determinant. From there, we know that we can multiply and subtract. So that means I'll be multiplying 4 times negative 1 and then subtracting from that the product of 6 and 2. Then this gives me 4 times negative 1, which is negative 4. Negative 6 times 2 is negative 12. And then combining those values, you'll end up with a final result of negative 16. Red, box it, people. There you have it. Just like that. We have just completed finding the determinant of problem number 4 using the multiply and subtract method. Now to have some fun with finding a triangular matrix from the original matrix and multiplying the elements of the main diagonal. So we're going to be rewriting this, showing that we're going to be finding the determinant of the matrix with the elements negative 1, 2, 6, and 4. So instead of going for this 2 again that we did in our first example, let's go ahead and create a triangular matrix with the zeros underneath the main diagonal this time. So I'm going to get a row operation that reads 6 times row 1 plus row 2, placing the result in row 2. And let's see what happens here. I know that my first row will remain unchanged, so I'm going to bring down the negative 1 and the 2. And then when it comes to rewriting the second row, we need to multiply the first row by 6. So 6 times negative 1 is negative 6. Negative 6 plus 6 is 0. 6 times 2 is 12, and then 12 plus 4 gives us 16. Then all we have to do is multiply the elements of the main diagonal. My main diagonal contains the elements negative 1 and 16. So that means we'll have negative 1 times 16 to give me a result of negative 16. Red, box it. Just like that, guys. And that completes example number 4. In our next fun fact, guys, if any 2 rows or any 2 columns of a determinant have corresponding entries that are equal, the value of the determinant is 0. All right, You see any identical rows or columns in your matrix and you're looking for the determinant, the answer is 0. You're welcome. All right, let's keep it going. Here we have example 5, and we have a 3 by 3 matrix. What does that mean for me? If I'm using the multiply and subtract method, that means I need to rewrite the first 2 columns. So I'll begin with -1, 0, 3, 1, 2, 4. And with that, I'm going to be taking the diagonals up to the left and multiplying them together first. So in order to find the determinant of B, we're going to then multiply -1 times 2 times 2 plus the product 1 times 3 times 3 plus the product of 2 times 0 times 4. And then we'll start subtracting the products going up to the right. So I'll have 3 times 2 times 2 minus 4 times 3 times -1 minus 2 times 0 times 1. And this is my setup for finding the determinant of matrix B. That means that I'll have the following products in play. So multiplying -1 times 2 is -2, -2 times 2 is -4. We'll be adding to that 9, then 0. Then we have -3 times 2 is -6, -6 times 2 is -12. From there, we'll have -4 times 3 is -12, -12 times -1 is +12. And then we'll have -2 times 0 is 0, 0 times 1 is 0. And these will be the values that we combine, guys. Combining my negatives together, I'll have -16. Then combining my positives together, I'll have 21. And when I find the result of this, my answer will be 5. Red, box it. Done and done. We have our result for problem example 5, guys. All right, continuing on, we have the second version of problem number 5, where we'll be finding a triangular matrix and then multiplying the elements in the main diagonal. Reviewing this problem, I already have a 0 underneath the main diagonal here. All I have to do is get a 0 where the 3 is and where the 4 is, and I'm done, guys. Therefore, in finding out the determinant of matrix B, I'm going to do the following row operation. I'm going to have 3 times row 1 plus row 3 and placing the result in row 3. Once again, I'm doing all of my multiplication to a different row other than the one I'm replacing. That means in this case, I'll be bringing down rows 1 and rows 2 unchanged. We'll have -1, 1, and 2. As well as 0, 2, and 3, and then multiplying row 1 times 3 and then adding it to row 3, I'll have 3 times -1 is -3. -3 plus 3 gives me 0. Then I'll have 3 times 1 is 3, 3 plus 4 is 7. Then I'll have 3 times 2 is 6, 6 plus 2 gives me a result of 8. Then next I'll want to get a 0 where the 7 is. In order to make that happen, I'm going to do the following row operation. I'll have -7 halves, row 2, plus row 3, placing the result in row 3. This means that my first 2 rows will go unchanged. I'll be bringing down -1, 1, 2, as well as bringing down 0, 2, and 3. Then what we'll do is we'll be multiplying -7 halves times 0 to give me 0, and then 0 plus 0 is 0. Then multiplying -7 halves times 2, that gives you -7, and -7 plus 7 is 0. Finally, we'll have -7 halves times 3. That gives you -21 halves. You'll be adding that to the element in row 3, which is 8. So let's write 8 as 16 halves. Once we combine that, you'll end up with -5 halves right here. Now that we have a triangular matrix, I'll be multiplying the elements in this main diagonal. And the determinant of matrix B will be the product of -1 2, and negative 5 halves. We know that the result will be positive because you have an even number of negative signs. And we also know that these 2's will cancel out. So therefore, 1 times 5 is just 5, and that's my answer. Red, box it. And that completes problem number 5 again, guys. 5 with an answer of 5. Let's move on to our next fun fact, which is Kramer's rule uses determinants to solve a system of equations. Many students always wonder, why should I learn how to do this strategy? Well, when it comes to determinants, one of the usages of determinants is solving a system of equations. So, using Kramer's rule, you'll be expected to find the determinants of many different types of matrices. So, that's one reason for learning how to do determinants, guys. Let's keep this train moving. All right, to problem number 6. As we have a 2 by 2 matrix. So with this 2 by 2 matrix, we're going to be going ahead and multiplying our diagonal to the left and subtracting from that the diagonal going up to the right. So I'll have 3 times 5 minus 2 times negative 3, and then multiplying and combining my terms together. 3 times 5 is always 15. Negative 2 times negative 3, that's positive 6 all day long, guys. You end up with 21. Red, box it. That's it. Just that fast, guys. These 2 by 2 matrices didn't even see it coming. Yeah, we got them. Sniped them. Moving on. Problem number 6 again. This time with the main diagonal, guys. As far as picking which way I want to go with this triangular matrix, I think I want to kill the 2 down here. So in order to make that happen, I need to multiply something times this 3 above it in order to make that happen. So what I can do is I can say 3 times what will equal to negative 2, because I need the value to be negative 2 in order to cancel out that positive 2 in that second row of our original matrix, right? Well, in solving for this, you'll find the value that you'll need to multiply that row by. And it turns out you need to multiply row 1 by negative 2/3 in order to come up with that fraction. So anytime you're not certain what value you need to multiply a row by, you can always use this setup here to find out what that value is. Knowing that I wanted the result of this product to be negative 2, I took the existing value that I had and I said I'm going to multiply it by a value. What that value is at the time, I did not know. So using algebra, I was able to solve for that unknown value and find out that I need to multiply the row by negative 2/3. Let's go ahead and put this work to good use. We'll say that negative 2/3 times row 1 plus row 2, and then rewriting that in row 2. So we have the following matrix now, guys. Row 1 is unchanging. We have the 3 and the negative 3 coming down, and what we'll be doing next is multiplying negative 2/3 times 3, which gives you negative 2, and then negative 2 plus 2 is 0. Then you'll be multiplying negative 2/3 times negative 3. Well, that makes a positive 2. And then 2 plus 5 gives you 7. Once we have this, we have our main diagonal in the triangular matrix that needs multiplying together in order to come up with our determinant. Remember that you'll find your main diagonal right here, and all you need to do in order to find the determinant is multiply those values together. So the determinant of our problem here is the result of 3 times 7, which is 21. Red, box it, people. Just like that. You cannot tell me that this is not fun. All right. So you could try. I mean, you could try, but no. This is pretty good, man. It's pretty good. It's good stuff right there. Let's keep going. Fun fact number 8. Determinants can be used to find the area of a triangle. Here's another reason why learning how to find the determinant can come in handy. Do you not know how many triangles there are on Earth? Won't you find out the area of those using determinants? There you go. Another way to utilize this skill that you're just picking up on and mastering. Let's continue. We have problem number 7, guys. And in problem number 7, we're asked to find the determinant of a 3 by 3 matrix, and so we shall. Remember, using the multiply and subtract method, we'll be going ahead and rewriting the first 2 columns. So I'll be bringing over 0, 3, 4, as well as 2, -1, and -4. It's then these diagonals that go up to the left that I'll be combining first and then coming back and subtracting the diagonals that are going up to the right. All right. This means that the determinant of matrix C is going to be the result of 0 times -1 times 1 plus 2 times 2 times 4 plus 1 times 3 times -4 minus 4 times -1 times 1 minus -4 times 2 times 0 minus 1 times 3 times 2. This is going to be my setup for finding the determinant of this 3 by 3 matrix. Let's go ahead and find out what these products are, guys. We'll have 0 times -1 is 0. 0 times 1 is still 0. Then you'll have 2 times 2 is 4. 4 times 4 gives us 16. Then from there, we'll have 1 times 3 is 3. 3 times -4 is -12. Then you'll have -4 times -1 is +4. 4 times 1 is +4. Then you'll have the opposite of -4 is 4. 4 times 2 is 8, and 8 times 0, well, that's just 0, guys. And then you'll have -1 times 3 is -3. -3 times 2 is -6. We'll want to combine these values next. So I'm going to stay consistent and combine my positives first. We'll have 16 plus 4 gives me 20. Then combining -12 and -6 gives me -18. And finally, 20 minus 18 is 2. Done and done, people. That's right. Red box it. Just like that, guys. That was multiply and subtract. For problem example 7, keeping it moving with finding the triangular matrix for example 7. So looking at this, guys, I noticed that the first element in the first row, it has 0. We don't have any matching rows. We don't have any matching columns. There's no zeros for any rows or columns. So more than likely, the result of this is not 0. That being the case, I want to make sure that this first number in the first column is not a 0. Therefore, I'm going to go ahead and take the line of least resistance, and it looks like the 1, 2, and 2 will be a lot easier to get rid of than the 3, 4, and -4. Yeah? Yeah. So let's go ahead and make this our first operation. We'll find the opposite of row 3, add that to row 1, placing the result in row 1. So that means we get to bring down the second and third row unchanged. We'll have 3, -1, and 2, as well as 4, -4, and 1. What we'll be doing in order to rewrite our first row is find the opposite of row 3 and adding row 1 to it. See, that'll get rid of that 1 in the first row, guys. So you'll have the opposite of 4 is -4. -4 plus 0 gives you -4. Then you'll have the opposite of -4 is +4. And then 4 plus 2 is 6. Then the opposite of 1 is -1. And -1 plus 1 gives you 0. So we're on our way to getting a triangular matrix with the 0 being in the upper right hand corner. All right, let's move on. We have 2 more values to make zeros. And what we'll do next is multiply row 3 by -2 and then add that to row 2, placing the result in row 2. All right, notice how I'm avoiding multiplying the row that I'm replacing, okay? That is the key to keeping the determinant unchanged. Also, I'm not swapping any rows or columns, and I'm also not worried about any factors because I'm not multiplying the row that I'm changing directly, okay? You can always add a multiple of another row to an existing row and rewrite it, and the determinant will not change. That's what I'm sticking to. That being the case, our first and third rows will not change. So we'll be bringing down -4, 6, 0, as well as for negative 4 and 1. Here we'll be multiplying negative 2 times 4 to give us negative 8, and then negative 8 plus 3 is negative 5. Then we'll have negative 2 times negative 4 is positive 8. 8 and negative 1 combine to give us 7. And then we'll have negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Okay, for my next magic trick, I need to find out what value I need to multiply 7 by in order to make the opposite of 6 so that I can get that final 0 here. So remember, I'm going to use algebra to find that out if I don't already know it. I'll have 7 times some number needs to equal to negative 6 in order for me to cancel out that positive 6 in the first row. If you solve for x in this case, you'll divide both sides by 7 to find out that the value that you need to multiply by is negative 6/7. Once again, algebra helping me out when I need it. So therefore, my new operation will be negative 6/7 row 2 plus row 1, putting the result in row 1, guys. That's what I want to do right now. So that means that row 2 and row 3 will go unchanged. So we'll bring down negative 5, 7, 0, 4, negative 4, and 1. So we want to multiply negative 6/7 times negative 5, then add that product to negative 4. So we'll show that here by having negative 6/7 times negative 5 minus 4, which will equal to 37, and then you'll have a negative 28/7. Combining that, you end up with positive 2/7, people, just like that. Then multiplying negative 6/7 times 7, that gives you negative 6. And then negative 6 plus 6 is 0. And then negative 6/7 times 0, it's 0. And 0 plus 0 is 0. All right, so the only one we had to get stressed out about was the first term. Okay, so now we have our triangular matrix, and we can multiply this main diagonal to find out our determinant. Therefore, the determinant of C equals to 2/7 times 7 times 1. The 7s will cancel out, and 2 times 1 is 2. Red, box it. Just like that, guys. And that completes problem number 7. Moving on to fun fact number 9. If the determinant of a matrix is non-zero, meaning the determinant is any other number but 0, then the matrix has an inverse. So matrices can have an inverse. Interesting. So I'm pretty sure you'll be seeing a video from FBT about that very soon. Link will be in the description very soon, if not now. We have problem number 8. And in problem number 8, we have a 2x2 matrix. Let us please kill this problem, guys. We have the determinant being the result of multiplying 2 times 8 minus negative 1 times 3. This gives us 16 plus 3, and the answer is 19. Red, box it. Red, boxing it, people. That was the multiply and subtract method for problem number 8. Moving along to our triangular matrix method here. That's right. Ready to multiply the main diagonal elements in order to get the determinant. I believe, I know, that I want to make a 0 right here where the 3 is. Yeah, just random choice. That's all. That being the case, I need to multiply 2 by something in order to get a negative 3. Well, in that case, I need to multiply by negative 3/2. So negative 3/2 row 2 plus row 1, placing the result in row 1 is what's going to happen. So that being the case, that means my second row will go unchanged. I'll bring down the negative 1 and the 2. And then I'll be multiplying row 2 by negative 3/2, adding that to row 1. So negative 3/2 times negative 1 is going to give me a positive 3/2. And then I want to add that to 8. So 8 written as a fraction is 16/2 with a common denominator of 2. So I end up with 19/2. Okay, so 19/2 will go here. Then I'm going to be multiplying negative 3/2 times 2 to give me negative 3. And then negative 3 plus 3 is 0. So we now have a triangular matrix with our main diagonal containing the values 19 halves and 2. Therefore, our determinant is going to be the product of 19 halves times 2. Well, in this case, your 2's will cancel out, and your answer is 19. Red. Box it, people. Just like that. That does it for problem number 8. Moving on. We have problem number 9. And in problem number 9, we have a 3 by 3 matrix. Yes, we do. And that means I'll be copying down the first 2 columns. I'll rewrite 0, -1, 2, as well as 1, 3, and 8. Yeah, I hate the 2 as well. Thank you. Okay, I thought it was just me. Nope. You're not doing any better. This is going to fly. It's going to have to. I'm not rewriting it again. Okay, from here, our determinant is going to be the result of combining all of the diagonals going up to the left, which are the products of 0, 3, and 3, adding to that 1, 2, and 2, adding to that 2, -1, and 8, then subtracting from that all of the diagonals going up to the right. So you'll have 2 times 3 times 2 minus 8 times 2 times 0 minus 3 times -1 times 1. Let's go ahead and simplify this, guys. You have 0 times 3 is 0. 3 times 0 is it's 0, guys. Then you'll have 1 times 2 is 2. 2 times 2 is 4. You'll have 2 times -1 is -2. -2 times 8 is -16. Then you'll have -2 times 3, that gives you -6. -6 times 2 is -12. Then you'll have -8 times 2 is -16. -16 times 0 is 0. And then you'll have -3 times -1 is +3. 3 times 1 gives you 3. From here, let's combine it together. If we combine all of our positives together, you'll have 7. Combining your negatives together, you'll have -28. This gives you a result of -21. Red. Box it. Red box it, people. There you go. That was problem number 9 using the multiply and subtract method for a 3 by 3 matrix. There you go. Moving on. We have problem number 9. Yes, we do. And we're going to do this using a triangular matrix. My first step here, observing what I have, is to decide whether I want this triangular matrix to have zeros beneath the main diagonal or zeros above the main diagonal. I lean towards smaller numbers, guys. Just saying. So that means I want to have zeros where the 1, the 2, and the 2 is. My first step is going to be the following. I'm going to have the opposite of row 2 plus row 1 going into row 1. Let's check it out. This means I'll be bringing down rows 2 and 3 unchanged. I have -1, 3, and 2. Here we go. The next row is 2, 8, 3. And then, in order to rewrite the first row, we're finding the opposite of row 2 and adding it to row 1. So the opposite of -1 is 1, and then 1 plus 0 gives you 1. The opposite of 3 is -3. -3 plus 1 is -2. The opposite of 2 is -2. -2 plus 2 is 0. Thank you. There you go. Next, I want to get a 0 where this 2 is, right here. And that means I'll be manipulating this value in the third row. So that means my row operation will be -2/3 row 3 plus row 2, placing the result in row 2, just like this. This means that I'll be bringing down the first and third rows unchanged. We'll have 1, -2, 0, as well as 2, 8, and 3. From here, I'll be multiplying 2/3 times 2. Okay, that gives me -4/3. All right, and then I want to combine that with -1. Well, -1 is -3/3 in this case. So I'll end up with -7/3 for this term right here. Then I'm going to be multiplying -2/3 times 8. So -2/3 times 8 gives me -16/3. And then combining that with 3, this gives me another negative 7/3, people. Just like that. Finally, I'll be multiplying negative 2/3 times 3. This gives me negative 2. And negative 2 plus 2 is 0. And there we go. We now only need to get a 0 where the negative 2 is. So doing a little algebra here, I can show that if I take negative 7/3 and multiply it times a number, I need that value to equal to positive 2. Well, by multiplying both sides by the reciprocal of negative 7/3, which is negative 3/7, you multiply this times both sides, you can find out exactly what that value needs to be. All right. So in canceling out all of this stuff, all that cancels out to leave your variable x. On the right side, you'll end up with negative 6/7 as the value you need to multiply the second row by in order to combine that with the first row to get your 0 that you're looking for. So that means that my next row operation is going to be negative 6/7 row 2 plus row 1, placing the result in row 1. And so here we go. We know that we're going to keep the second and third rows alone. That leaves us with negative 7/3, negative 7/3, 0, 2, 8, and 3. Fix the 3. 3 is a little better, but no. It looked like a duck trying to kiss someone. Then what we're going to do is this. We'll be multiplying negative 6/7 times negative 7/3. What does that look like? You'll have, I think I know exactly what it'll look like. It'll look like positive 2, but let's just prove it. You'll have negative 6/7 times negative 7/3. See, your 7s will cancel out. A negative times a negative is a positive, and 3 goes into 6 twice. Yeah, that's 2. That's the whole reason why we did that earlier step, right? I hate the equal sign. We have to fix that. It looked like a great-grandfather Z. Now, what we're going to do is this. Distributing the negative 6/7 to each of the terms in the second row, adding that to the first row, you'll have 2. 2 plus 1 is 3. Thank you. Thank you. I'll be here all week. Next, you're multiplying negative 6/7 times negative 7/3 to get 2 again. And 2 and negative 2 combine to give you 0, guys. And then negative 6/7 times 0 is your friend, because it's 0. And 0 plus 0 is still 0. There you go. There you go. You now have a triangular matrix, people. And with your newfound triangular matrix, you just need to multiply the elements in the main diagonal. This means that our determinant is going to be the product of 3 times negative 7/3 times 3. We know that when you have an odd number of negative signs, the result will be negative, and these 3's right here will cancel out. So you'll have 7 times 3 to give you negative 21 as your final answer. Red box it. That's right, people. Red box it. That was problem number 9. In problem number 10, we have a 4x4 matrix, guys. And we do not have a preferred method. When I say we, I mean me. There is not a preferred method that I want to use other than the triangular matrix method of multiplying the elements in the main diagonal. That means I'm not doing any multiply and subtract method because I don't think one exists. What I will be doing is focusing on getting zeros either above or beneath the main diagonal. What troubles me initially is these 2 zeros right here on the main diagonal. I think my first operations, guys, is going to be combining rows together in order to make sure that I don't have any zeros here. That troubles me. It's just in the way. Okay? All right, party people. If you're ready, I'm ready. My first row operation is going to be to combine row 3 and row 2 together, placing the result in row 2. That's what I'll be doing first. Okay? Just like this. So we'll be bringing down rows 1, 3, and 4 as they will go unchanged. So I'll have 4, 0, 0, 2, as well as 2, 4, 0, and 1, and 0, 0, 1, 2. I will be combining row 3 and row 2 together. In other words, adding those 2 rows together, rewriting it in row 2. We'll have negative 1 and 2 combined to give us 1. We'll have 0 and 4 combined to give you 4. 4. 3 and 0 combine to give you 3, and 0 and 1 combine to give you 1. And this is my new row 2, people. My next row operation is to add row 4 plus row 3, putting the result in row 3. So let's hook that up right now. Okay, that means that only the third row is going to be changed. So bring down rows 1, 2, and 4 unchanged. So I'll have 4, 0, 0, 2, 1, 4, 3, 1, 0, 0, 1, 2. And then combining row 4 and row 3 together, in other words, adding those together, 2 plus 0 is 2. 4 plus 0 is 4, 0 plus 1 is 1, and 1 plus 2 is 3. See, I feel a lot better now knowing that I have values along the main diagonal now. Now I'm going to be focusing on getting values either underneath the main diagonal or above the main diagonal as zeros. And I'm going to choose to have all of my zeros above the main diagonal here. In my next operation, I'll be finding the opposite of row 4, adding that to row 1, putting the result in row 1. Just like this, people. So that means that I'll be bringing down the second, third, and fourth rows unchanged. So we'll have 1, 4, 3, and 1, 2, 4, 1, and 3, as well as 0, 0, 1, and 2. We'll be taking the opposite of 0, which is 0. 0 plus 4 gives you 4. 0 plus 0 is 0. The opposite of 1 is negative 1. Negative 1 plus 0 is negative 1. The opposite of 2 is negative 2. Negative 2 plus 2 is 0. Next, we'll be taking negative 3 times row 2 plus row 3 and placing the result in row 3. 1, 2, 3, 4, and 1, 2, 3, 4. We'll be bringing down rows 1, 2, and 4 as they go unchanged. I'll have 4, 0, negative 1, and 0. And I'll also have 1, 4, 3, 1. And then the fourth row is 0, 0, 1, 2. From here, we need to multiply row 2 times 3 and add it to row 3. So 1 times negative 3 is negative 3, and 2 give us negative 1. Then negative 3 times 4 is negative 12. Negative 12 and 4 give you negative 8. Then you'll have negative 3 times 3 is negative 9. Negative 9 plus 1 is also negative 8. And then you'll have negative 3 times 1 is negative 3. And negative 3 plus 3 gives you 0. All right. Keeping it moving, our next step is going to be multiplying negative 1/2 times row 4 plus row 2, placing the result in row 2. This is my next row operation. Since I'm only changing the second row, I can bring down rows 1, 3, and 4. We'll have 4, 0, negative 1, 0. Then negative 1, that's a bad negative, negative 1, negative 8, and 0, as well as 0, 0, 1, 2. We'll be taking negative 1/2 of row 4, so negative 1/2 times 0 is 0, and then 0 plus 1 is 1. Then negative 1/2 of 0 is 0, 0 plus 4 is 4. Negative 1/2 of 1 is negative 1/2, and negative 1/2 and 3, which is 6/2, combine to give you 5/2. All right, so we'll have 5/2 here. Then you'll have negative 1/2 of 2, which is negative 1, and negative 1 plus 1 is 0. Our next operation is going to be 5/2 row 1 plus row 2, placing the result in row 2. Here we go with that. All right, so only changing the second row, bring down rows 1, 3, and 4. So I'll have 4, 0, negative 1, 0, as well as negative 1, negative 8, and 0, as well as 0, 0, 1, 2. Then we'll be multiplying 5/2 times row 1. So 5/2 times 4, then adding that to 1. This gives you 2 goes into 4 twice. 5 times 2 is 10. 10 plus 1, sorry, just 11. So there we go with that. So you end up with 11 here. Then multiplying 5 halves times 0 is 0, and then 0 plus 4 is 4. Then multiplying 5 halves times -1 is -5 halves, and -5 halves plus 5 halves is 0. And then 5 halves times 0 is 0, and then 0 plus 0 is 0. So you have 11, 4, 0, and 0 here for your new row 2. Hate this 11. Gotta fix it. All right, it's better. It's better. Our next operation is going to be to multiply 2 times row 2. Add that to row 3, placing the result in row 3. 1, 2, 3, 4. 1, 2, 3, 4. Counting lines, guys. So we're going to be bringing down rows 1, 2, and 4. We'll have 4, 0, -1, 0. We'll also have 11, 4, 0, 0, as well as 0, 0, 1, 2. In order to get the new third row, you're going to be multiplying 2 times 11 is 22, and 22 and -1 give you 21. Then you'll have 2 times 4 is 8, and then 8 and -8 give you 0. Then you'll have 2 times 0 and -8 give you -8. And then 2 times 0 is 0 plus 0 gives you 0. The reason why I did this step right here, guys, is because my goal is to try to eliminate the -1 in the first row. I truly couldn't eliminate the -1 in the first row with having a term right here in this third row. I had to eliminate this first, the second element in the third row, so that I can utilize this to generate a 0 in the first row. Okay, so I was thinking a step ahead as far as why I needed to do this step right here. My next operation is to multiply -1/8 times row 3 and add that to row 1, placing the result in row 1. 1, 2, 3, 4. There you go, guys. We are going to bring down rows 2, 3, and 4 as those go unchanged. We'll have 11, 4, 0, and 0. We'll have 21, 0, -8, and 0. We'll have 0, 0, 1, 2. In order to come up with our new row 1, you'll say 21 times -1/8. So that's going to be -21/8 here. We're going to add that to row 1, which is 4. So that 4 is 32/8. And that combines to give you 11/8. So 11/8 goes here. Then multiplying -1/8 times 0 is 0, and 0 plus 0 is 0. And finally, multiplying -1/8 times -8 gives you a +1. And 1 plus -1 is 0. And then, of course, this last element in row 3, -1/8 times 0 is 0. 0 plus 0 is 0. And now you have a triangular matrix, people. And with this triangular matrix, we'll be focusing on the main diagonal, just like that. That took us 8 steps, guys, if you were wondering. So we're going to be multiplying 11/8 times 4 times -8 times 2. I've done it in less than 8 steps, guys. However, I had to utilize some of the other rules, like swapping rows or multiplying a row by a certain value, and I didn't want to do that because it changes the outcome of the determinant. When it gets to this final step of multiplying together, I don't want to have to remember what I did to get here. Okay, so that's why I'm making sure and strategizing and using only rules that don't change the answer whatsoever. That being the case, these 8s will cancel out to give me -1 here, and 11 times 4 is 44. 44 times -1 is -44, and -44 times 2 gives me a result of -88, which is the answer. Red box it, people. That was problem number 10, and how to utilize the strategies that have been shown in the video in order to solve for a 4x4 matrix. Yeah, that was pretty good. That completes this video on how to find the determinant of a matrix, people. Please give us a thumbs up. Please give me some feedback in the comment section. Let me know which method you preferred. Also, on that last problem, let me know how many steps it took you to solve that problem using the strategies that I showed in the video, okay? And if you're able to donate, please do so, as that helps us bring you more free math tutorials from Fort Bend Tutoring and myself, Mr. Whitt. And do not forget to subscribe to the YouTube channel Fort Bend Tutoring. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.